Hey there, Math Moment Makers. John here from Make Math Moments. And in this video, we're going to talk about the 4 stages of mastery and how you can use those in any of your topics to strengthen and deepen your students' understanding and learning of mathematics. If this is the first time you have been to our channel, our videos, hit the subscribe button over on YouTube if you're watching us on YouTube. If you are watching us on Facebook, you can hit the bell or get over to YouTube so that you can get subscribed, and which you get notification of our videos when we post new ones. In this video, we're talking about the 4 stages of mastery, and what you're going to see is actually a clip, actually a lesson from our full online course, our 12-week online course. We're pulling it from the arc, from its place in our learning platform, and we're putting it here free for you to look at on YouTube. And it's a lesson on those 4 stages of mastery and how you can use it for any of your topics. We specifically go through multiplication in the video to show you examples. But really looking forward to you kind of diving into this learning. And stay tuned afterwards. I can show you a little bit about the workshop itself, the 12-week program, and where this lesson lives. This is actually in the 4th module. This is the first lesson in the 4th module. So dive in. Here we go.
Hi friends, Kyle here. We've spent a significant amount of time in the previous modules focusing on sparking curiosity and building grit, resilience, and perseverance in order to fuel sense making. As we start to dive deeper into teaching through problem solving to build understanding, it's probably a good idea for us to spend some time reflecting on what it means to learn and understand new information, and to explore the stages that humans typically go through when learning something new. According to the Merriam-Webster Dictionary, learn means to gain knowledge or understanding of or skill in by study, instruction, or experience. This suggests that knowledge and understanding can actually be different. When we look at knowledge, we see it defined as the fact or condition of knowing something with familiarity gained through experience or association, or an acquaintance with or understanding of a science, art, or technique, the fact or condition of being aware of something, or finally, the range of one's information or understanding. This definition suggests that knowledge could be considered knowing some facts or information, almost like scratching the surface of learning. For example, when the definition uses the word like familiarity or acquaintance, but the definition then goes on to describe knowledge as possibly something deeper when the word understanding is being used. When we look at the definition of understanding, we see that having an understanding means to have a mental grasp, the power of comprehending, the power to make experience intelligible. This definition seems much more robust than that of knowledge alone.
Side by side, we can see the subtle but important differences. One might go as far as to say that to have an understanding, you must have knowledge, but knowledge does not always include understanding. However, I think it's important to note that I'm not suggesting that students must know everything before they can begin building an understanding. I believe knowledge and understanding can be built simultaneously, although we do have to be intentional to ensure that there's a balance. You do require some knowledge before we can work on understanding. However, we don't want to get carried away on memorizing tons of math ideas before attempting to understand them. So I think it's important to highlight that a very important part of learning mathematics involves gaining knowledge and understanding simultaneously. Now that we have a deeper understanding of the learning of knowledge and understanding in math class, let's look at how we can go about helping our students gain knowledge and understanding. When exploring research on learning, you'll find a learning theory that seems to have many different names. Some of the many names are the stages of competence, the stages of learning, the stages of mastery, and many more. However, the learning model we'll be exploring was first introduced by Martin M. Broadwell in 1969, and he called it the 4 stages of teaching. Regardless of what you choose to call this model, I'm going to refer to it as the stages of mastery, and we're going to have a look to see if we can apply it to see how some students might be learning mathematics in our classroom. Similar to how we represented the hero's journey on attention versus time graph, we're going to model the stages of mastery on a competence versus consciousness graph. I know, 2 big words to wrap our heads around, but let's unpack what I mean by this. If we look at the origin, we'll see this is where most learners begin their learning journey. And this is because they typically start both unconscious of the new learning and they're also incompetent. Many often refer to this stage as being unconsciously incompetent. Doesn't sound very flattering at all. And the learner might say, I don't know what I don't know. And I'm sure you've heard that expression many times before. When we speak of ignorance, it's because we actually don't know what it is we don't know. So that's where we're starting here. Let's take a look at how this might apply to learning new mathematics. Here we have a set of candies, and the new concept that we're aiming to learn is multiplication. If the prompt given to the learner is how many candies are there, a learner who is unconsciously incompetent might think to count the candies, and thus their response might sound something like, I counted each candy, and there's 21 total. Despite the fact that the learner is unconsciously incompetent with using multiplication or multiplicative thinking, the student is able to reach into his or her toolbox of prior knowledge to use their one-to-one correspondence skills from counting and quantity. The beauty of mathematics is that we have the ability to let students use their prior knowledge to help push them forward from unconsciously incompetent to some sort of new learning. Let's have a look at what the next stage looks like. As you can imagine, in order to become competent or at least aware of their competence, students must become conscious to this new learning that they're working towards. We call this the consciously incompetent stage. This is where the learner might say, I know what I don't know, and they have now an awareness of this new learning, but they aren't feeling quite competent. Now, this is a tricky stage because we're actively trying to build both the student competence of a new idea while building their awareness or their consciousness at the same time. So let's revisit the same situation from our previous stage and apply it to this stage. We have the same situation with the same prompt asking the student how many candies there are. The difference is here that the student might be aware that there's some other way to determine how many candies there are, but they aren't sure how to go about doing it. So they end up counting the candies using one-to-one correspondence, just like they did in the previous stage. The student response might sound very similar or exactly the same as the student in the unconsciously incompetent stage, and that makes our jobs difficult to help us determine where they are in their learning journey. However, the beauty is that if we have a well-planned lesson with the specific learning goal in mind, we can help students cruise through these first 2 stages by helping them become aware or conscious of the new learning while building their competence simultaneously. If we do this effectively by thinking about the student trajectory or progression of learning related to a specific math concept, we can help most students get to a place pretty close to the next stage that we call consciously competent. This is where the student might say, I know what I know, and it starts to show, which is a great place to be. Let's have a look at what the same example might look like now. Again, we have the same prompt with the same number of candies, except if the students are aware and able or consciously competent, then students may be able to see that there are 3 groups of 7 candies. And then they can skip count, or their flexibility with addition and subtraction can help them to arrive at an answer. The student response might be that they skip counted by 7, so there's 21 total, or some other strategy based on their number flexibility. Now, this is where a lot of us might be surprised. Wouldn't a student who's consciously competent with multiplication just know that 3 groups of 7, or 3 times 7 is 21 candies? That's what I thought for the majority of my teaching career. However, I now realize that if I'm consciously competent, it means that I'm actually having to do some thinking using my conceptual understanding to come up with an answer. Don't worry, we'll get to the 3 times 7 is 21 candy stage next. Oh, and we should also mention that there's many different possible student thinking strategies that would land a student somewhere around this consciously competent stage. It's not a one approach fits all sort of deal. Okay, so let's move on from consciously competent to our next stage, unconsciously competent. This is where the student might say, I simply go because of what I know. So, looking at the same prompt with the same number of candies, students at the unconsciously competent stage might still be seeing and thinking the same thing as those in the previous stage, like seeing 3 groups of 7. However, they built in the automaticity to almost instantly know that the result is 21 based on the connections that they've made, unitizing and building their flexibility with numbers. So while the student response might sound very similar to that at the previous stage, the strategy would actually be more connected to their automaticity built with multiplication rather than to have to actually think about unitizing. This is where we would align the automaticity students build over time with the unconsciously competent stage. So let's quickly recap all 4 of the stages of mastery. Students typically begin at the unconsciously incompetent stage, then they become aware of what they don't know and they move up to the consciously incompetent stage. We then hopefully zoom fairly quickly through the first 2 stages because students are so flexible with their prior concepts necessary to build this new learning. And if this is true, students are going to find themselves at the 3rd stage where they're consciously competent, where they know what they know and it shows. Finally, students have worked with this new idea so much that they've made so many connections and associations in their brain that they begin to show signs of unconscious competence, where the automaticity begins to take over. And then the cycle can begin over again as we add another layer of abstraction or complexity. In this case, an example might be moving from multiplication onto proportional relationships, where we can take multiplicative thinking a step further. While some believe that reaching that unconsciously competent stage would suggest that the learner has reached mastery, others suggest that the journey towards mastery of a concept or idea does not end there, and I tend to agree. John Bergman, a pioneer in the flipped learning movement at johnbergman.com, also believes that there's a 5th stage to achieving mastery. Both he and many others believe that simply reaching the level of unconscious competence is not the same as mastery. In order to reach mastery, you must become flexible with the idea, and in order to do this, you must be reflective and thus very conscious of what it is that you're doing and learning. If you are consciously reflective and through this deep thought you begin to build mastery of an idea, that might put this stage somewhere to the top right corner of this graph. And I might name this stage the consciously masterful stage. Obviously, the process would look different for every new idea we're learning. For example, the graph wouldn't consist of straight lines, but probably something more like a smooth curve. For some ideas, you may stay in one stage much longer than another, and the level of consciousness and competence might vary along that learning journey. So here's what that might look like for our example of multiplication. Again, same prompt, same number of candies, so a student at the consciously masterful stage might still be thinking that there's 7 groups of 3 candies. However, they would probably be able to articulate this in a variety of ways, like maybe 5 groups of 3 candies plus 2 groups of 3 candies, which is the same as 15 plus 6, or 21 candies in total. The strategy that this student used is the distributive property, which again demonstrates a much deeper understanding of how multiplication works than simply knowing that 3 groups of 7 is 21 candies through automaticity. Now, I want to be clear that we're not trying to push students to always show their use of multiple representations on every problem. Otherwise, students will become quickly annoyed and that they may even start to dislike math class because of this. However, verbally asking student questions will help you determine where they are and how deep their understanding is related to a concept. And this is very important and must be included where appropriate throughout the learning process. So there we have it, the stages of mastery. Here's a quick peek at each stage and the example we had used throughout this lesson. Now, before we move on to our call to action for this lesson, I wanted to share a quick quote from Phil Darrow, one of the authors of the Common Core State Standards for Mathematics, and a colleague who I've had the honor of co-presenting with at NCTM this past year. In one of our conversations, the idea of mastery came up, and his perspective really impacted my thinking of mastery and how it applies to learning mathematics. He said, "I think it's worth emphasizing that students in every grade need to develop expertise in comprehending concrete situations related to their grade level math, and that is even right through high school math. They then need to develop an expertise in representing their comprehension diagrammatically and symbolically. I see this as active agency on the student's part, actively creating representations of increasing abstractness for the purpose of taking advantage of the amazing flexibility and elegance of abstract representations." He goes on to say that he mentions expertise development because it's an apprenticeship kind of learning, not a mastery kind of learning. So I might argue that rather than calling these stages of mastery, we might follow Phil's lead and call these stages of expertise. Something else I really appreciated from his quote is his call to action for students to develop expertise concretely, diagrammatically, and symbolically in every grade from K through 12. While the research on the use of concrete representations first, followed by diagrammatic or visual representations, and then finally symbolic representations is not new, there are still many classrooms outside of the very early grades that are rushing to symbolic notation before students have developed that competence with concrete and visual representations. In our next lesson, we'll be taking a trip from number sense to algebra, focusing on concrete, visual, and symbolic representations. So be sure to keep the stages of expertise in mind as we continue through this module. So now it's time. On to our call to action for this lesson. Jon and I want you to select a concept that you'll be teaching in the next week. And then, using the Stages of Expertise template, we want you to brainstorm what each of the stages would look like, including possible student thinking, the student response, and the math concept that the student used at that stage. Then, we want you to add a comment in the discussion area to share what you came up with. We're so excited to dive deeper into Module 4, so get at this call to action, and we'll see you in the next lesson. Bye for now.
All right, Math Moment Makers, that was Kyle talking all about the 4 stages of mastery, and that was one lesson from Module 4 in our 12-week full online course, the Making Math Moments That Matter online course. I just want to show you where that lesson lives inside of our platform. I'm going to show you, I'm just going to bring up my screen right here. Here we go. There's that lesson right there. This is you just kind of watched that video in our learning platform. This was the 4.1 stages of mastery, and that's one of the lessons in Module 4. If I come over to the side here and drop down, now I've crossed them off because I've completed them, but that was lesson 1 out of Module 4. We've got 6 lessons in Module 4, which is all about teaching through problem solving. That's that lesson, that module there. If I jump to Module 4, you can see that we've got an intro video there, and the materials are all there. So for example, if I go back to that lesson that you just watched, we had an action item right at the end of that video, which asks you to kind of use our template to start planning your lessons. And our past students, we've had 1,100 students through the program in the past, and they dive right into that learning. They're taking that to heart, so they're using our template to walk through that stages of expertise, the stages of mastery, and planning it out for their students in their class. Again, that's one lesson in many lessons. We have 6 modules in this course, and it's our full platform, our full program that teaches you how to build resilient problem solvers through our 3-part framework. Whereas Module 1 kind of introduces you to the framework and what you can expect. Module 2 is all about building curiosity and how do we do that and what are the best ways to do that. Module 3 is about teaching through a productive struggle and how do you create a productive struggle in your classroom so that kids can learn deeper and we can build great problem solvers that way. You had a glimpse of one lesson from Module 4, which is about teaching through problem solving. And Module 5, over here on the side here, I'm referring to, Module 5 is all about adapting the 5 practices for orchestrating productive mathematical discussions into your room. Like, what are the teacher moves necessary to, make all of this happen? So all your learning previous to the 5 modules, it's like, how do you make that happen in your class? What do you have to do before? What do you have to do during lesson? What do you have to do after? And then in our 6th module here at the bottom, actually, I got to zoom out here. Let me scroll down. In the 6th module, we have all about planning and assessment. And then in final, we have a bonus module on how to spark curiosity and fuel sense making when you're teaching remotely. So we've adopted this program to teach during our pandemic the way we've been doing it. So we got 6 modules plus the bonus module 7 inside the workshop. So if you're interested, definitely check that out at makemathmoments.com/online workshop. I'm going to bring up that page, the instruction or the information page on the online workshop. You can register if it's open. If you're watching this live when this video goes out, it's open right now, and you can register. Otherwise, you can join the wait list if you're watching this at a later time. But really looking forward to seeing the next cohort come in. So if you enjoyed this video, please hit the subscribe button and hit the like button, because that helps this video get in front of more educators, and we can start to change the way mathematics is taught in our classrooms. But we'll see you in the next Making Math Moments video. Take care.